Take a moment and just observe. A leaf drifting gently to the ground, a speeding train vanishing into the horizon, or the silent rhythm of your breath. Motion is not just out there, it's happening within you right now. Your heart beats, blood flows, and air rushes in and out of your lungs. Even the earth beneath your feet is in constant motion, rotating once every 24 hours, while orbiting the sun at an incredible speed. So here's the big question. How do we describe motion precisely and scientifically? Welcome to your first step into the world of physics, motion in a straight line. So what exactly is motion? At its core, motion is simply a change in position with respect to time. But to describe it scientifically, we need more than just observation. We need a reference point. Think of it like this. To say something has moved, we must know from where to where and in what time frame. That's why we use a coordinate system, a unit of time, and a chosen direction. And to keep things simple, this chapter zooms in on just one kind of motion, rectilinear motion. That is, motion in a straight line. It's the perfect starting point to explore how objects move. In the real world, every object has a shape and size, but in physics, we often take a clever shortcut. We simplify moving objects as point objects, tiny dots that carry all the motion information we need. Why? Because when an object travels a distance much greater than its size, its shape becomes irrelevant. Imagine a train covering 500 kilometers. Do we track every window and door? Of course not. We treat the entire train as a single point, and that's enough to describe its motion accurately. Let's bring this idea to life with a classic textbook-style example. Picture yourself riding a bicycle along a straight, quiet road. You start at point A and reach point B in 10 minutes. As time passes, your position changes steadily in one direction. This is what we call rectilinear motion. And because the distance you travel is much greater than your body or your bicycle, we treat the whole system as a single point object. Simple, efficient, and scientifically sound. This chapter marks the beginning of kinematics, the science of describing how things move. Here, we won't worry about what causes motion. That's a question for later. For now, our focus is on how motion happens. We'll use 3 key tools. Displacement tells us how far something moves and in which direction. Velocity reveals how quickly that position is changing. Acceleration measures how the velocity itself changes over time. It's like building the grammar of motion before diving into the story behind it. Why do we need to study motion? Because understanding motion gives us the power to predict, design, and improve the world around us. Engineers use motion equations to create safer, faster vehicles. Athletes rely on motion analysis to sharpen performance down to the millisecond. Astronomers calculate the motion of planets and satellites to navigate space. And yes, even something as critical as a car's braking distance can be accurately predicted using simple motion equations. So, motion isn't just theory, it's the foundation of real-world innovation. Let's end with a fascinating example that shows just how fast we're all moving through space. Without even realizing it, we're going to calculate the average speed of the Earth as it orbits the Sun. The formula we'll use is speed equals 2 multiplied by pi, multiplied by capital R, and divided by capital T. Let's calculate the distance Earth travels in 1 year. Distance equals 2 multiplied by 3.14, multiplied by 1.5, multiplied by 10 raised to the power 11, which gives us 9.42 times 10 raised to the power 11 meters. Now let's compute the time Earth takes to complete one orbit. Spelled out, T equals 365 days multiplied by 24 hours per day, multiplied by 60 minutes per hour, multiplied by 60 seconds per minute. That equals 3.15 times 10 raised to the power 7 seconds. Now plug those values into our speed formula. Speed equals 9.42 multiplied by 10 raised to the power 11, divided by 3.15 multiplied by 10 raised to the power 7. Doing the division gives us 3.0 times 10 raised to the power 4 meters per second. So the average speed of Earth is about 30,000 meters per second, or in simpler terms, 30 kilometers every second. Yes, you heard that right. We're all orbiting the sun at a speed of 30 kilometers per second, and we don't feel a thing. That's the elegance of motion, immense, silent, and mathematically beautiful.